everyone and welcome to this video. And in this video what I'm going to do is that I'll make you familiar with the principal component analysis algorithm, which is another yet powerful unsupervised learning algorithms. Principal component analysis is a kind of algorithm that just make 3D data to that reduces the dimensionality, or that reduces the dimensions. So definitely we'll cover all the things that you need to know to get started with the principal component analysis. Okay, the implementation part will be coming soon of the principal component analysis. First, let's take a look at details. And also please give me the comment down below if you like the motivation as I give in start of the video. That's a feedback. Okay, so without this time, let's get into it now. So first of all, what is a principal component analysis? This is very easy to answer. Principal component analysis is a dimensionality reduction algorithm, or we can say method, that often used to reduce the dimensions of the data. To reduce the dimensions, this is the main thing, the dimensions of a large data set reduces the dimensions of variables or features, and it's transferring the whole large data set's information to the small data set without losing any kind of information. Just the same thing that I'm going to talk about now. So let's take more into detail. Let's say this is my large data set. What the principal component analysis does is that, let's say this is my large data set, and what it does, let's say x1, x2, x3, x4, x5, these are my features or variables. These are my variables. So let me write it again so that it can show up beautiful. So let's take an example. Let's say we have x1, x2, x3, x4, and these are my features. Each and every are my features, and what this principal component analysis does is that it's simply, we have of this kind of dimension data set, and what it does, it compress it or reduce the dimensionality or the variables of this data set, and we are left with x1, and here for these three, all the information contained in this will go on to this, and thus we get x1 as our principal component. And then it is much more easier to take any algorithm and perform or analyze or explore the data set. And in simple terms, I can say that a principal component analysis is an algorithm that reduces the number of variables or of features of a large data set while preserving the information. And this might be really very easy to understand. Again, I'm recapitulating. What the principal component analysis does is that it reduces the number of the variables or the features of the large data set into small dimensions while preserving the left of the information, or we can say that it preserves let's say 96% of the information of the data into one variable, and it left out and 4% for them. So definitely we'll go with x1. So this might be very easy to understand what does a principal component analysis is. Now I've written down 5 steps to perform principal component analysis. So if you follow these 5 steps, you will be developing a principal component analysis. The first thing first, we have normalization. That I've just talked about a normalization or a standardization. What does it mean? I have made a detailed video of feature scaling. If you're following this course, then you might be familiar with feature scaling, and if not, I would very much recommend to go on to my feature scaling video and watch the video. The link will be in the I button or in the description box below, and if I forget to down a link in the description box below, you can go on my ML course playlist and then check out the feature scaling. The video is very important for this principal component analysis. Okay, so now what this for the recapitulation, let's say what the feature scaling does is that it simply bring all the variables on the same scale. If we do not let's say if we do not do feature scaling, what does it do? Let's say we have 3 kilometers and 3,000 meters. An algorithm will understand 3 kilometer is less than the 3,000 meters. That's not true. Let's say 4,000 meters, and that's not true. Yeah, no. So for bringing up all the features onto the same scale, we do something called the feature scaling, and the formula for the same is the xi minus mean, which is mu, upon standard deviation. Okay, and you can calculate this kind of standard deviation. Just I've given you the brief introduction. If you're following up my course, you'll be very much familiar with this. If not, I'll be recommending you go on to my feature scaling video. That's a very, very important video. Okay, so the first step for developing a principal component analysis is that you should do feature scaling. Okay, now the next step is covariance matrix computation. What does it mean? What we do is how the variables of the input data x are varying from the mean which we have just taken with respect to each other. Let's say this is my input data x1. Let's x1, okay, here, and how much this is varying from our input, which is a mu. Okay, for that we take a covariance matrix, and by taking the covariance matrix, this is a second step that will actually be helpful for us. Okay, so it's simply how the data, the input data have the relationship between the input data and the mean. Some simple thing. So let me write this as, so the relationship between let me write BW between the input data and the mean with respect to each other. This is pretty much easy. Now let's take a look at a computation for the covariance matrix computation. It's a D by D symmetric matrix. What is D here? D here is the kind of dimensions. D here is the dimensions. So we'll take one example and this will be very clear. And it's a symmetric matrix. Now let's take an example so that you can get more intuition on how do we calculate the covariance matrix. Okay, so here is an example so the example is for example, we have a 3D data set, okay, with the 3 features x, y, and z. Okay, what we will do, let's make a matrix here, COV, covariance of x, comma, x, because we have x, which is a dimension, and here and the same thing, that input data. Then we have covariance of x, and here we have y because we have x, y, and z. Okay, so we have covariance of x and z. Again, we have a next thing here. We have a covariance of y comma x, covariance of y comma y, covariance of y comma z. Then we have the covariance of z comma x, covariance of z comma y, then covariance of z comma z. Okay, So we have made a 3 by 3 matrix. That's what I'm telling. That is 3 and 3. Here's the D. Okay, dimensions. Okay, and for the details here, if we are taking covariance of x comma x, so what we are doing, it's equivalent. So let me write in a different color. So the covariance of x comma x is equivalent to the variance of x. Again, for the covariance of y is equals to the variance of y. It's a diagonally which has a equally. Okay, so covariance of y comma y is equals to the variance of y. Then we have our favorite z, and covariance of z is equals to the variance of z. Okay, and for the details, this is pretty easy, that the diagonals are equal to the variance. Okay, here's something like that. Okay, pretty much clear. Now you have taken the covariance matrix. How does it happen? And if you want to get more intuition behind a covariance matrix computation, I would like to recommend this video, HTTPS YouTube LOC. The link will be in the description down box below, or you can copy from the notes and paste it on the browser and go there and watch the videos. Okay, so now the video recommended is this. So if you want to get more into details of covariance, I would like to suggest you this video. Now we have computed the computation matrix, or a covariance computation matrix. Now how does it help us, or what it does? Something like that. Okay, so now let's take a look at what it gives. After taking out the covariance, what it gives? It tells us if we have positive, then the positive variable or positive thing, that positive, let's say variables, then the variables are directly correlated. I think you might be familiar with directly proportional and inversely proportional in your physics. So what does it mean? That in directly proportional, if the something is increasing, then the other thing is also increasing. It simply means if an object, let's do some kind of physics. So if an object, let's say a ball, is increasing, then if it is directly proportional, then other ball will be also increasing. And this is called directly proportional. Directly, I'm not going to go detail in the physics. If you want me to make, please comment down below. Okay, so this is directly proportional. And if you say an object is decreasing but another object is increasing, so one object is decreasing and one object is increasing, so it's a inversely proportional. So we can conclude that if it is positive, then the variables are directly correlated. It means they are increasing together and they are decreasing together. And if they are inversely correlated, then the one is increasing and the other one is decreasing. Okay, and if you have any problem, be sure to comment down below. These two things very much clear. Till now we had done around 2 steps. Now let's go on to the step number 3. Now we have standardized the data or normalized the data. We have computed the covariance matrix. Now it's time for computing the principal components. It simply means we'll talk about principal component analysis just in a second. Okay, so what we'll do, we'll compute the eigenvectors and eigenvalues for principal components. The thing I'm going to stop you here is that I'll strongly suggest, if you want to go in mathematically, I strongly suggest to go onto the 3 blue 1 brown, 3 blue, 1 brown. I think you might be familiar with this guy. He's doing very much good thing. Okay, so you just go here and just take a look at the eigenvectors and eigenvalues, and you'll be understanding pretty much easy. But the thing is that you don't need that just now. Okay, so don't worry about it, just carry up with this video. Okay, so the computation for eigenvectors and values for the principal components. So what is the principal components? They are the new variables that are constructed as a linear combinations or the mixed of the initial variables. I have written this very dirty kind of thing here, that this would not be very much clear to you, this kind of equation. So let's make it more easy. Okay, so now let's take a pen here, and yeah, so what is actually do what is principal components? Let's say x1, x2, x3, x4, x5. Okay, x5. And what it does is that it simply take all this information and put this as much as they can into this one variables, and then it contains, let's say, 96%, and this contains 94%. Okay, so we'll definitely go with the 96%. So for more clarity, let's take an example. So here is an example. So in this example, we have v1 and v2, and we have taken out the eigenvalues lambda 1 and lambda 2. And what we do is that we simply take in the descending order, the eigenvalues. So the lambda 1 is greater than the lambda 2. It simply means that, for example, it contains more amount of information, rather than this. So let's say it contains 96% of the variance data, and it contains the 4% of the variance data. Okay, so what we'll do, we will simply go with this lambda 1 and with this eigenvalues. So what we'll do, we will simply take a look at the eigenvalues. And how do we calculate eigenvalues? We first take it out of okay, you can take a look at the eigenvectors and values at a 3 blue 1 brown. Okay, so we just take it out the eigenvalues and just compare this to in the descending order, and then we choose the largest or the first to win in the descending order, lambda 1. So we can tell that the lambda 1 contains a good amount of information against the kind of lambda 2 or lambda 3, etc, etc, etc. So we'll definitely go with the lambda 1 because lambda 1 is greater than lambda 2. Okay, pretty much easy. Now till now we have computed the principal components. How we compute it? We first reduce the number of variables into 1. Now, how do we eliminate? Now what we'll do, we have choose whether to keep all this or discard. This statement suggests we choose whether to keep all the components or discard of lesser significance. It simply suggests us if we have, let's say previous example, we have 4% in the V2. So we will take out the V1 because it has 96%, it has 96%, and what we'll do, we'll discard those who has lesser significance, or we can say low eigenvalues, and then we'll form the remaining ones as a matrix of a vectors. So we call it as a feature vector. Okay, pretty much easy. So what we will do is that we simply discard those who has lesser or a small eigenvalues, and will form the matrix of the vectors, and that's called a feature vector. I'm writing in bold. Okay, so that's called a feature vector. And now what we have done, we have eliminated V1 and V2. V1 has a 96 information of the variance data, and V2 has a kind of the 4%. So what we'll do, we will eliminate V2. It's completely optional, but what we'll do, we'll eliminate this V2 and we are left with V1, as we have reduced the dimensionality of V1. Now we have developed our principal component. It simply means that we had just reduced the dimensionality of our model or data set. Okay, now, but there is some kind of problem that the input data are just now, now we have developed, just now our input data will be on the same scale or on the same axis. So for bringing up our input data onto the principal component, principal axis, or and hence it's called principal component analysis. So for that, for bringing up the kind of the input data from the original axis to the kind of principal axis. Okay, so for that we have an again mathematical intuition about it. For the final data, what we'll do, we'll find the product or the feature vector transpose times the original data transpose. But what original data? The data that we have standardized, or we have done a feature scaling on that. So I have to write feature scale data, not the original, for the feature scale data. And for transpose, again recapitulating, so let's say this is my vector, and if I transpose, let's say V equals to, if I transpose V transpose, so what I'll do, A, B, C, D. So this is how you transpose it. Okay, so we have in step 1 we have feature scaled or standardized. In step 2 we have the computed the recast, in step 2 we have covariance computation, and step 3 we have computed the dimensionality reduction, and then in step 4 we have just recast the data or a feature vector, and in step 5 we have recast the data. Okay, so that was it for this principal component, and I hope that you developed a very good algorithm till now, and you are finding it enjoying and engaging. The notes in the description down box below, be sure to review it, and also take your copy and pen and write the notes that I just marked down. Okay, so I think that's it for this video. It's already 22 minutes, and I'll be catching up in the next video. Before leaving on this channel, if you want to hear me again, please be sure to subscribe this YouTube channel and press the notification bell. So thank you for watching this video. I'll be catching up in the next video. Till then, bye bye.